So, thank you very much, everybody, for being here, and to the organizer also for inviting me to this fantastic event. So yes, my purpose today is to talk about theory of Carroll Flux-Balance laws for flat space holography, which will be first a scientific talk, but also a talk aimed at some mathematical elegance. And I deserve it because we are in Florence, and you know that Florence is attracting many artists, even musicians. I remember, for instance, that Felix Mendelssohn was visiting Florence for a couple of weeks and was very much inspired, both musically and at the level of painting, by this city. So I have to aim a bit at mathematical elegance. So this talk is based on a paper entitled Carolian Holographic Derivation of BMS Flux Balance Laws that we published recently with Marius Petropoulos at École Polytechnique, Simon Pécard, Mathieu Villat. And this is only the beginning of a bigger program, so there is more to come, also in collaboration with Ismaël Alouche Lalali and Mathieu Beauvillain, who will be here next week. So this is the plan of my talk, so divided into 3 acts, like an opera performance, if you wish. So first of all, I would like to remind some things about flat space holography, which are maybe unnecessary for most of the audience, but let me be complete. Then I will study a bit more some aspects of the boundary geometry that I will use for the third point, in which I will explain you how to derive actually gravitational dynamical laws from purely Carolian considerations. The pointer annoys me, so voilà. Ah non, hein? Voilà. Okay, let's go. So first of all, this is the definition I will take for what we are interested in this workshop, which is holography, and more particularly flat space holography. So for me, and I think for many of us, holography, which is a promising route toward quantum gravity, can be, so the paradigm behind that can be summarized in this sentence: gravity in a given space-time region can be accorded to the codimension 1 boundary of that region. So I will not insult you in reminding you why we think it will be working. But let me just remind you that up to now, the only really explicit realization of this holographic paradigm we have at disposal has been done for ADS spacetime, so with strictly negative cosmological constant. And unfortunately for theoretical physicists as we are, but fortunately for human beings that we are not living in ADS. We are living in de Sitter, but as you know, everything that touches far or close to de Sitter is problematic. So let me discard the cosmological constant for the time being, because also it's in line with the program of this workshop. And let me say you that, in fact, what is attracting the most of interest nowadays in the theoretical physics community is the vanishing cosmological constant case, which is still useful for a large class of physical situations, from collider physics to gravitational wave astronomy. So, but before that, I would like to remind you some aspects that are useful in what we master very well, by which I mean ADS CFT. So in ADS CFT, at least at the classical level, we can do the following bulk analysis in 4 dimensions. So I will be 4 dimensions for this talk. So thanks to the process of conformal compactification, we have a natural definition of an holographic screen, which is space-like infinity, and which is a conformal boundary. I will come back on this later, but this conformality is fundamentally rooted to the conformal compactification process. So to make things clear, on such a space-time, you can set a Gaussian set of Gaussian normal coordinates starting from this hypersurface at infinity, which will be situated at this coordinate rho going to 0, as follows. It's a Pfefferman-Graham coordinate system, and you can define the boundary metric that I write here, G, like the limit of here the transverse metric with respect to this space-like foliation. In this setup, there has been a lot of work in understanding the variational principle underlying this theory of gravity. And up to a holographic renormalization process that I will not review here because it will take me a lot of time, you can find a version of the gravitational action after renormalization which obey the following very beautiful formula. So its first variation is actually giving you this symplectic pairing between the boundary metric J and another piece of the metric, which comes at the third subleading order in this transverse metric, in which we will call a stress tensor of your boundary theory, simply because this definition. So you can do a purely boundary analysis and see what can be extracted from it. So if you assume that there exists an effective action living on your boundary, we depend on some fields phi and coupled to the geometry, which is encoded into your conformal metric G, and such that it obeys this relation with respect to the bulk gravitational action when the boundary field are on shell, you get a relation between a source in your dual theory and the response, which is the stress tensor. Then if you add this a symmetry principle behind that, meaning that you ask for diffeomorphism invariance on the boundary and Weil invariance, because you have here access to only conformal class of metric at the boundary, you will get the conservation of this stress tensor and its condition of trace-freeness. And these two equations are, in fact, the only relevant Einstein equation that you have on the boundary. So, purely on the boundary, demanding for relatively simple symmetries, which are Diffeo and Weil, you recover the Einstein equation without using any bulk argument. So, this allows you to define this, what I call the zero piece of the holographic dictionary, that this T mu nu is in fact the energy momentum tensor for your boundary theory, which is a CFT. This is the famous Bala-Subramanian and Cross result. And this result, which is very important, and in fact, lacks in flat space holography. So my goal today is to explain you how we can Bala-Subramanian crossing flat space holography. Okay? So I really like this slide because it puts in comparison what we know very well, so ADS, so which is basically our comfort zone, and what is our future, so flat space holography. And you have all the relevant differences to understand why flat space holography is a bit more complicated than ADS. First, if you set a certain set of boundary conditions which are Dirichlet, and you choose, again, Gaussian normal coordinates on the boundary, you can always put your boundary metric in this form. So you see that here, the lambda plays, so the cosmological constant, sorry, plays a bit the role of effective speed of light, meaning that when you will bring it to zero, you will get a null manifold, which is null infinity. The boundary physics, therefore, is no longer Lorentzian, but a bit more fancy, and is called Carrollian. The gravitational dynamics, which is encoded in ADS by this really simple relativistic equation, will be replaced by more fancy equations, which are the so-called BMS Flux-Balance law that I review quickly in the next slide. Also, if you demand that your boundary, so which is no null infinity, so the boundary of this conformal diamond is assorted with Dirichlet-like boundary conditions, so meaning that the boundary metric is purely Minkowski, these boundary conditions are naturally leaky because you have a non-conservation of the BMS charge of the bound, which is also something that is known for most of the audience, I hope. And then the relevant symmetries are no longer a finite group like the conformal group, but now an infinite dimensional group, which is also rooted in the fact that the boundary manifold has a null direction. Okay? So, the normal vector to infinity now is null because you have no cosmological constant, so the boundary metric is degenerate. It's a property of any null manifold, in fact, in general relativity, so nothing new under the sun. Since it's repelled to infinity, like in ADS, you don't have a simple differential manifold, but it is endowed with a conformal structure, or more precisely, a Weil structure. And here, since you have two objects, because now the metric is degenerate, you have also this vector upsilon. It's not a V, it's a upsilon, that will scale also with this Weil factor, and it will scale as follows, as prescribed by general relativity. So the relevant symmetries are BMS. So let me quickly review what BMS is. So if you ask to preserve this kind of structure, basically, you will ask that your infinitesimal generator of diffeomorphism on the boundary will solve this equation for a certain B of psi. And then if you set some again, Gaussian null normal coordinates on the boundary, which are called the Bondi-Sachs coordinates, you see that the general solution of these equations is as follows. So the YA is basically representing the conformal Killing vectors on the sphere, so the Lorentz group. But you have here, where you can find usually the translation, in fact, a parameter which depends arbitrarily on the coordinate on the sphere. So you have an infinity of super translations. And this is again due, as I already said, to the null nature of the boundary. So yes, just to set everything in one consistent talk. Whenever a piece of your metric goes to zero, so induce some non-trivial radical of your metric form, basically you are changing the nature of the relativity you are playing with. So meaning that the induced relativity at the boundary is in fact the slow boost limit of special relativity, where you favorize the space-like intervals over the time-like ones. If you do that, Jean-Marc Lévy-Leblond tells you that it's equivalent, mathematically speaking at least, to send the effective p dot light to zero, which is exactly what happens at null infinity. So null infinity is intrinsically Carrollian. This limit induces ultralocality because basically, since the speed of light is the inverse slope of this light cone here, it closes on the time-like axis. So you have actually one unique field of observer, which is this vector epsilon I was mentioning. Therefore, in this kind of relativity, which is a bit bizarre, but that's life, huh? Space is absolute and the boost is only in the time direction. Okay with this concept? I know it's a bit iconoclastic, but that's the nature of null infinity. So if you want to do flat space holography, you have to face that. Or you stay in EDS and everything is fine for you. So now, at null infinity, you can solve Einstein's equation, and that's a really old story, starting with actually Trotman in 59, and followed by the works of Bondi, etc. You can solve the asymptotic Einstein's equation, and then you will notice that the gravitational field is described, roughly speaking, by three independent fields, which are the mass aspect, so the distribution of gravitational energy on the sphere surrounding an asymptotically inertial observer, in physical terms, the angular momentum aspect, which is the equivalent but for angular momentum, and also the shear of outgoing null rays that are depicted here in red. And also a more important tensor is in fact its time derivative, so the derivative along the flow of this vector epsilon is the news that I will call here curly n. So when you have this tool to play with, you can solve Einstein's equation, and they lead to this kind of relations. And unlike in EDS CFT, or more exactly in EDS to be precise, in classical EDS, these are not conservation equations. You see, for instance, here the mass, which plays the role of energy, is not conserved, so this right-hand side is not zero. This is a total derivative, but crucially, this, which is called the Bondi mass loss term, is there, and you have to understand why it's there, where it comes from, if you want to do some serious flat space holography. Okay, so why do we care? Because, after 20 or almost 30 years of ADS-CFT correspondence, we would like also to test a bit the limit of the holographic paradigm. Here, for flat space, you have non-conservation of the charge, which means that you have to add some kind of external sources that will produce the right-hand side of this equation, basically. So you can do it by hand. We did it with Romain a couple of years ago, but it does not solve the principal question: what's the nature of the source, and are we still doing holography if we feed the dual theory with arbitrary stuff. Note that also this concept of leaky boundary condition can also be useful in a DSCFT, and I will be able I will be happy, sorry, to discuss with interested people, but that's not the point of this talk. Second, as I told you, we don't have, yes, please, Atul. Yeah.
Picking the symplectics. If your charges are not conserved, is it possible that your definition of the charge is slightly off? Maybe you made a mistake in picking the symplectic structure or something else?
No, there is no mistake because physically, this flux has a physical meaning, you know. This flux is observed, for instance, in gravitational interferometers. So these equations come from the symplectic structure of general relativity, and making an error in the symplectic structure, meaning I have chosen badly my boundary term. But what you can show is that there is no boundary term that can cancel these sourcing terms. They are physical.
But if they're not conserved, then they don't generate symmetry actions?
They
as
generate
charges?
symmetry actions under a refined version of the Dirac bracket.
Okay, so
Yes.
there's some sense. Okay.
Yes. So that makes one question.
Okay.
Any other question? So if not, let me continue. So yes. So since we don't have anything like the Balasubramanian cross construction in flat space holography, we have basically, I don't want to say nothing, but we don't have to me at least, the zero layer of what holography is that at least semi-classically, you can define what encodes the symmetry at the boundary, which is traditionally in a DSCFT, a stress tensor that generates a word identity, blah, blah, you know the story. Here, we don't have that in flat space holography. And also, since these equations are not usual and raise concern, as Atul Swan a few minutes ago, we would like to understand the fundamental principle behind these flux balance laws without referring to Einstein's equation. Otherwise, it's cheating. So let me also say that it's applicable to any null boundary. For instance, if you formulate holography in a space-time where you have a black hole horizon, you will have also a null manifold at the boundary to take into account. And then what we are discussing is also relevant for that case. Maybe more interesting for some of you is that our work can have applications for what is called the Carrollian scattering amplitude that we defined also with Romain a couple of years ago and that were studied in particular by Lionel, Atul, etc. a couple of years ago. So these Carrollian scattering amplitudes, in fact, result in a construction that allows to encode any massless scattering from the point of view of null infinity. So, and I will refer to Lionel's, Romain's, and Atul's talk next week, where they are going to expand a bit on that from the twistor perspective, or I don't know, but so there will be some comment about that next week. So then we would like to have some kind of Carroll invariant effective generating functional for these massless scattering amplitudes encoded from a Carrollian perspective. And we hope that our work can pave the way towards the derivation of such an action. Okay? So this is the end of my long introduction, I know, but I think it's necessary. So any question at this point? No, so if not, let us study a bit the boundary geometry I will need. So first of all, let me remind you a bit of what is called the conformal compactification. So the conformal compactification introduced by Roger Penrose in '63 actually, and beautifully used in many papers afterwards, postulate the existence of a diffeomorphism between a certain manifold and another manifold, which is called physical. And this diffeomorphism is able to remove the pole at infinity in the metric. So the physical geometry will be this capital G tilde, So this is my metric, and the metric on the unphysical spacetime will be this G without a tilde. And I have this omega square between both that is strictly positive in the bulk of my unphysical metric, but which vanishes at the boundary. So now in this compactified spacetime, I can attach this boundary omega equals to 0 to my bulk spacetime, and then I have a notion of boundary, bulk, and also conformal infinity. The price to pay in this construction is that I can change my defining function here omega by any non-vanishing factor. So in fact, I'm inducing an infinite class of Weil rescaling in the process. So which means that that's really important, because I think it's not enough appreciated in the specialized literature, is that one physical metric is not linked to one unphysical metric, but to a conformal class of metric. And the most salient consequence of that is that if you encode the gravitational field on the physical spacetime in the Levi-Civita connection associated with this G tilde, in fact, you will induce through the diffeomorphism one Levi-Civita in the unphysical spacetime associated with one metric, but this will not be covariant under this symmetry, which is a purely kinematical symmetry that you don't want to break. That's why I think that people finding a non-vanishing Weil charge are easily breaking the symmetry and are basically happy to find charges that are non-zero, basically because a symmetry is broken. So it's not what you have to do, right? You have to keep this Weil covariance, and for that, actually, you play with the null normal covector of your boundary, which is d omega by definition, plus a piece which vanishes at the boundary, but which introduces here a field A, one form, that transforms inhomogeneously under Weil rescalings, and which allows you to define what is called the Weil-Levi-Civita connection. So a connection that preserves the metric up to a Weil rescaling, which is absorbed by this A. This is a very old concept introduced by Wald in 1918, but I think it's the right way to understand gravity in asymptotically flat spacetime. So that's it for the bulk gravitational field. So now let's give the two main consequences of Einstein's equation. So if you assume that G tilde and not G, be careful, G tilde solves Einstein's equation on the physical spacetime, then first, it's not a surprise, but the conformal boundary is a codimension one null hypersurface. So it verifies this. I will still denote by upsilon my field of observer, so which is in more geometric terms the null generators of the null manifold scry, and its dual clock form, tau, which is a form that when it eats upsilon returns 1. Then I have a geometric definition of what the cut of scry is. So a cut of scry is an horizontal space at the point of scry generated by the vector v, which are in the kernel of the clock form. And I will assume that this space of a space-like direction has the topology of the sphere. And to make things easy in this talk, I will pick an orthonormal basis and its dual cobasis for the rest of the talk. So the metric is basically this on scry. So just to give you a terminology and notation, so I will call it the Carroll-Cartan frame and the dual coframe, and I will write it with capital letters, which will encompass the 0, which is the direction of upsilon and tau. So the time-like direction, if you want, it's a null, but okay, the null direction, intrinsically it's null. And A equals 1 and 2 will be the two direction on the sphere. The second consequence of a chain equation is that so it's a bit technical, but in a beautiful words, the Weingarten of scry is proportional to identity. So it's a very pedantic way of saying it, but that's the correct way. A more pedestrian way is that the shear of the generator of scry vanishes. And from that, what you can show is that if you pull back basically the bulk Weil-Levi-Civita connection, you get a torsion-free and Weil-Carroll compatible connection, meaning that it preserves the metric and the Carrollian vector, so the field of observer, up to their respective Weil transformation. And the small alpha here is merely the pullback of the bulk Weyl connection capital A. So again, as a matter of notation, I will expand this connection into the Carroll Cartan frame, and I will write the connection coefficient as follows, and I will store them in connection one forms. To avoid clutter, I will also redefine my covariant derivative here by a Weyl covariant derivative by removing basically the Weyl connection and the weight of the field, so that actually if this curly D operator acts on the Weyl weight W field, it returns a Weyl weight, just a matter of notation. So any question up to now on the formalism? Yes, Massimo?
Does not change by volume.
Which one? The nabla or the No, the curly D is defined precisely such as the fact it does not change the Weyl weight. Of course, if you compute, let me write something. If you compute this object, so here it's an index-free notation, meaning that this has the shape of a one form, right? But if I contract it with a base vector, this has also a Weyl weight 1, so this object will be Weyl W plus 1. But that's just the technicity. The important point is that it's covariant. Okay? Any other question? So if not, let me discuss a bit the symmetries, because after all, it's the most important thing. So you have the spatial rotation that basically rotate the horizontal basis and keeping invariant the vertical one, so the field of observer and the clock form. And the connection for this spatial rotation is encoded by the the omega, little a, little b piece of the connection. You have also this kind of transformation because you can change arbitrarily of clock form. And this should remind you the following transformation I wrote before, which was this. So this is the local version of a Carroll boost, if you wish. And the connection for this Carroll boost, which are afterwards, and Simon will explain that to you next week, are associated with super translation. So this should not be broken. And then you have to keep arbitrary this part of the connection, which encode actually the Carroll boost connection. You have the same for Weyl rescaling. So I'm sorry for this typo. It's a delta. There is no delta and no minus actually. It's just BAI, Adrien. So you have the Weyl transformation of the Carroll Cartan frame, and the Weyl connection is encoded by this purely vertical piece and the trace of the purely horizontal piece. The diffeomorphism acts also on the boundary, simply like Lie derivative. And a note that I can make here is that you see that the omega A0 is invariant, or more properly covariant, under all the transformations. In fact, what we can show is that is the connection for the Galilean boost that have been killed when you send the cosmological constant to 0. So
Sorry.
Yes.
Is this comment related to the fact that one can map or relate the Galilei algebra with central extension equal to 0 with the Carroll one?
Exactly. Yes. Because in fact, if you transpose all your matrices, you will basically exchange this connection one form for this one, and then since this was the connection for Galilean boost, you will recover the Galilean boost in that way, etc. So if you work in that kind of Carroll Cartan frame, you can also define a Galilei Cartan frame, which is basically the same. So meaning that your metric and cometric looks like as follows. It's basically this, which is the symmetrized tensorial product, and you have the inverse metric, which is basically that. And this is common for Galilei or Carroll. The only difference when you work in this frame is precisely what you call connection and what is not.
Right.
So if you say that the connection for my boost is this, you are Carrollian. If you say that it's that, it's Galilean. Okay? So that's a bit the power of the splitting formalism that Marios and collaborators have been developing for many years now. It's this kind of parallel between a Galilean and Carrollian structure, which is more evident, more manifest in this setting. So now let's discuss about the connection itself. We know that the connection preserves the metric and the Carrollian vector up to a while rescaling. Fine. We know that it's torsion-free. So are these conditions sufficient to determine the connection? In the case of Riemannian manifold, the answer is yes. It's the fundamental theorem of Riemannian geometry. But on Carrollian manifold, no, because you don't have an inverse metric, which implies this equation. So this is a part of the torsion, and this is the parallel transport of the Carrollian vector and the Carrollian metric. And you see that if you prescribe these spin quantities and also the torsion, you can run into absurdity because you have also this term, which is purely geometric and which encodes, in fact, the extrinsic curvature of cuts along the field of observation. So the fact is that because you have here an obstruction to define in an independent way a symmetric transverse tensor, so a symmetric tensor on the sphere, that means that, in fact, at the end of the day, your connection will have some degrees of freedom. By degrees of freedom, I mean some part of the connection that are not determined from geometry. These degrees of freedom also constitute a transverse symmetric tensor. So in 3 dimensions, the transversity is 2 dimensions, so meaning 2 plus 1, and it will be encoded in this part.
Excuse me.
Yes.
Maybe let me make the following comment that in Galilei occurs the same thing.
Exactly.
But there you are safe because there is a central extension on the Galilei algebra to Bartman, but not here.
No, that's the thing. So just to make to follow your comment, actually in the Galilean case, this object will not be determined. This is here a 2 form. So, but that's a 2 form over the whole manifold. So in 3 dimensions, it makes 3 components. So you see, it's the same number of degrees of freedom, but encoded in a very different way, which makes things more convenient, as you said, in the Galilean case. Because there you can ask for the so-called Newtonian connection, that this object is closed, and therefore F is the exact derivative of a field. And then you have a symmetry on top of that, because this is the potential for F, but this potential can be basically shifted by a constant, I think. Some say, no, not even a constant, any function. And this, no, okay, the derivative of a function. Sorry, so the external derivative of a function. And this, in fact, on the show is this U1 symmetry related to the central extension. Okay, but yeah. So, but just to make the comment that this is exactly the boost connection for Galilean boost, the connection for Galilean boost, sorry. Here, the ambiguity is in the boost connection for Carrollian boost. And sorry for the double pleonasm. So now I can present you the explicit solution for these equations. I don't ask you to remind you every detail, but just that everything is fixed up to this part. But what is this field actually? From the Bull point of view, it's related to the deviation tensor of null geodesics arriving at Scry. So it's kind of normal that it's not a boundary object. In fact, it's a bulk object. And it has been noticed already by Carroll and Ashtekar in their seminal work. But again, that's something that has not been, to my taste, sufficiently appreciated in the literature, because people, when they are doing Carrollian stuff, work always with a connection that breaks explicitly the boost symmetry by setting this to 0, because it's an ambiguity, so I can set it to 0. 9. Verboten. Strictly verboten. And Simon will also talk about that further next week. Okay, so now I have everything to wrap up. I think in 5 minutes. So now the lesson we have deduced so far from what I'm telling you is that we have to work in the conformally compactified spacetime. So which means that we have a huge bunch of symmetries at the boundary that seem unrelated. But you can ask, where is BMS in your story, Adrien? But BMS is simply emerging after a boundary gauge fixing, as Simon will explain you. So for the moment, I'm not fixing any gauge, anything. So my symmetries are the Carroll group, meaning so the Carroll, sorry, the local Carroll algebra, the homogeneous Carrollian algebra in 3 dimensions, meaning the rotations, the Carroll boost, the diffeomorphism, and the Weil transformation. And also, you don't have to insist on your Lorentzian intuition because of the following points. First, as soon as your charges are non-conserved, the very definition of a stress tensor, an energy momentum tensor, is a bit elusive. And that dates back to the seminal paper of Wald and Zupas in 1919, but also to Barnish, Troussard, etc. And many papers of Marius, and Marius will talk about these specificities in his talk next week as well. Even the flat limit of the Brown-York energy momentum tensor of ADS is defined. We showed it with Romain and Geoffrey a couple of years ago, but it was also clear within Marius formalism. Another salient point is that now the Carroll connections are not entirely fixed by background geometry, so you have to introduce them as extra data that you will vary on the boundary. So an equivalent statement is that there exist some external sources on top of the geometry at Scry, as advocated by Cédric Troussard in 15, Wolfgang Wieland as well, and our paper with Romain a bit later. Oh, sorry. So now, unlike in EDS, where you will just find the first 2 terms, so the term related to the fields phi, which are, if you wish, describing the microscopic expression of your theory, and which I don't know for the moment because I'm in an effective field theory setting, so I don't care about this microscopic content, but they are there actually. And the energy momentum tensor that I will define in a minute. Unlike in EDS, where you just have these 2 terms, you have an extra term where you vary the connection and you introduce some fields that respond to this variation. So the first term here with capital TA defines the Carrollian momenta, and I will expand them in the Carroll-Cartan frame as follows. So capital pi is the energy, capital pi A is the energy flux, PA is the momentum, and this 2-index tensor is the stress tensor. So this is known, but now I have to introduce, as I said, this response to the variation of the connection, which are called hypermomenta. These are vector fields, and these are unavoidable since part of the connection, at least, is extrinsic to the boundary. So, okay, if you do that, you can ask, as usual, for the invariance of this boundary action under each symmetry. The boost symmetry gives you that, so which means that your energy flux is purely coming from the hypermomenta. So you have some kind of geometric redshift, but no matter energy flux. The rotation and Weil are giving you some condition on the antisymmetric part of the stress tensor and the trace of the energy momentum tensor as usual, again perturbed by the hypermomenta. And the most important equation, if you ask for diffeomorphism invariance, which is what will be the reflection of the conservation equation in ADS, but for flat space, for asymptotically flat space time, these are these equations, where the R here is the Riemann curvature 2 form associated with this connection, curly T. And the very important point, already studied by Duval and Kunsel in 74, is that if this connection is not completely determined by the geometry, this right-hand side cannot be recast as a total divergence. So you have genuine flux-balance law. There is no choice of symplectic structure that allows you to reabsorb, if you wish, this right-hand side into a left-hand side. Because of this peculiarity of Carrollian connection. So do I have time to prove this equation for you, or should I conclude? It's up to you. Okay, so it will be quick. So I control the variation of my action with a diffeomorphism, and I set the microscopic fields on shell. So I get this. I basically expand the Lie derivative using Cartan's magic formula. I integrate by part using this particular relation that you can check. And it looks covariant with respect to scribe, but in fact, since you don't have any inverse metric, you have to split between the time and the space direction to obtain this relation, but it's true. You can check it as an exercise. And then, so you inject everything into this equation and you use the fact that the connection is torsion-free and Weil-Carroll compatible. And then you get this equation. So you see that the first term is what you want, this. The second is the contraction with the Riemann tensor. And the third one makes appear completely naked, without any pudeur, nothing, the connection one form. But the connection one form is multiplied by this tensorial object. And this tensorial object looks like all the conditions we have put on your boundary theory by virtue of the symmetries. And it is the case, actually, because you see that Carroll boost invariants say that the A0 component of this tensor vanishes. The antisymmetric part of the special projection of this tensor vanishes as well by rotation invariance. And Weil invariants say that it's traceless. So this term actually vanishes because what remains in this coefficient is just the following: by Carroll-Weil compatibility. And you see that the fact that omega is ambiguous does not play any role in this derivation. So this remains this equation where psi A, the diffeomorphism parameter, here is completely arbitrary. So the bracket here vanishes, hence the result. Okay? It's really beautiful. Huh? I should not say that myself, but I'm really happy to say to see this beautifulness, because actually these equations are nothing but the BMS Flux-Balance equation written in a very compact and elegant format. To reach the equation I was showing you at the beginning of my talk, we have to prescribe a minimal holographic dictionary like in ATS. So you have to give the fact that the boundary is 3D and shear-free, conformal Carroll manifold, okay, it's intended. The Carrollian momenta will be also matched with some subleading parts in the metric, arriving at the same order as in ADS, so meaning the third subleading order, and the hypermomenta are present only if the radiative pieces are present, so meaning if some outgoing geodesics are arriving at scribe. And for more details, again, I send you to Simon's talk, which will be giving you more details about the gauge fixing and also the precise expression and the BMS charge that can be prescribed through this procedure. So just as a concluding comment, since we have flux balance laws, I already said that the notion of energy momentum tensor is a bit elusive because we have a natural ambiguity in separating charge and flux. Again, it dates back to this seminal paper by Wald and Zupas, which has been used a lot of time in the relevant flat space literature afterwards. And it comes basically from this observation: if your flux term contains a total derivative, you can always absorb it into the stress tensor, and then you change what you call flux and what you call charge. So our procedure, and actually no mathematical procedure, can fix you this ambiguity for you. You have to, as Wald and Zupas said in their seminal paper, you have to demand additional requirements on your flux, such like vanishing for a class of physical situations that are non-radiative, etc. And for more details on the definition of the energy momentum tensor in the Carrollian setting, please refer to Mario's talk next week. So some open avenues before concluding my talk. So we would like to explore the link with ADS CFT by performing an asymptotically flat limit, which has also been beautifully performed in the case of Carrollian amplitudes by Romain and Lionel and also many brilliant people in Oxford. We would like also to understand the link without a kind of Brown-York energy momentum tensor for Scry, because to the best of my knowledge, this construction only exists in this paper by Flanagan, Chandrasekaran, and friends for finite distance null hypersurfaces. And also the link with an avatar of the holographic renormalization in flat space. And finally, our ultimate goal is to use the expression of our hypermomenta, which will be displayed by Simon next week, to prescribe or to have a bit of control on the microscopic theory for the degrees of freedom in connection, which is ultimately proposed to provide an action principle for the Carolian amplitudes. And with that, I will conclude, and as we said in Florence, vi ringrazio per la cortese attenzione.
Thank you.
Are there more questions, comments?
Yes.
So did I understand correctly? You're saying, as an example at least, that the stress tensor, this boundary stress tensor, is not conserved.
No,
That one was conserved.
it's not conserved.
Oh, okay, okay. So
Not conserved.
yeah, okay, good. So in standard ADS CFT, it is conserved, and that's why you can say that you have an open-closed coupling that takes the form integral of h mu nu t mu nu, where h mu nu is the bulk metric perturbation's boundary value,
Exactly.
and that source is the stress tensor. And you can write that coupling because that coupling is gauge invariant because the stress tensor is conserved. So in this case, you can't even say that your boundary stress tensor is the operator dual to a graviton in the bulk. You can't have that holographic interpretation, or it has to be modified somehow, and I'm wondering how you would
Okay.
modify.
To answer to your question, it will require a bit more of work, but I can give some element of response. Actually, what I consider as a graviton is here, actually, and not here in this case. Because the thing is that in flat space, you have something a bit peculiar happening, is that you can have boundary graviton arriving at the boundary, to be precise, without having a fluctuation of the boundary metric. What fluctuates, so the boundary value of the field is the shear, and not the boundary metric. So, and for me, the shear is over there. So, meaning that for me, what encodes the amplitudes, and in particular the Carolian amplitude, is this piece of the action. This encodes, if you wish, the massive, or how to say that, the stationary sector, if you want. So the one that can be already captured by an analysis of the coadjoint orbits of BMS and the formulation of a geometric action as Romain and Glenn did a couple of years ago. So long story short, this is the geometric action part, if you want, and this is, for me, the radiative part of the action.
So what is capital omega in there? Is
So
that
capital omega is the response of a variation of the connection. So in particular, sorry Simon, but I will have to spoil. So in particular, this term, one of the piece of this term is this one, because this is part of omega 0a, and this is the response, and the response is the news. And here you find back the HTK-Streubel presymplectic period.
I see. So you're saying the
Yes,
bulk.
it's okay. That's because Simon will explain that in full detail, so that's why I was not explaining that here. But this piece contains the HTK-Streubel, and in fact, it contains just that, up to geometric refinement, ensuring Weil covariance, different Weil covariance, Carolian covariance, etc. But that's just decoration, right? The real physical part, when you H fixed a la BMS, is this one.
So the news is the boundary, the analog of the boundary operator instead of the stress.
Yes, yes, and which is sound, right? Because in celestial CFT, you define your boundary stress tensor from the moment of the news, so it has some. Okay, it rings a bell even for celestial people.
Somebody else? Oh.
In your formula, you don't specify what are the fall-off boundary conditions at the two ends of Scry. So
Yeah.
is anything assumed, any particular fall-off to make this formula well-defined?
So for the moment, my considerations are only local on Scry, meaning that to prescribe this fall-off, maybe we would need to have access to maybe an example of these theories and computing this action explicitly and see what is diverging. But for the moment, I could prescribe any fancy boundary condition at the end of Scry and find the proper counterterm to cancel the divergences. So it just, yeah.
Maybe let me rephrase it. If you substitute in that formula some standard fall-off conditions, like what you get from perturbatively from gravitational scattering, would you get that the variation is well-defined?
Depends, the variation or the action itself. Because the variation will never be zero.
Well-defined, not infinite.
I can make it finite, yes. I can make it finite. Yeah. But that's again work in progress. But the thing is that if you prescribe the fall-off for the shear and therefore for the shear or disconnection and therefore the response, which is roughly speaking the news, in the formalism you are using, everything is covariant under all the symmetries I displayed you. So in particular, we will not have the usual problems of divergences due to the action of superrotation, etc. Because the formalism is already taking into account all the the authentic term as counter terms. If you give me more fancy boundary condition, I can add a corner term to decide this boundary action and see if it will normalize or not. But that will be tied to the precise formulation of your boundary theory, I should say. But that's a very interesting point.
So in flat space, you have an infinite tower of flux balance laws, and they are related to the celestial symmetries. So is there a hope to derive these flux balance laws in the same way?
Okay. I have multiple answers to this really expected question. And the one I would like to give here will be a bit provocative, is that I don't care. Why? Because since I can formulate this kind of equation on any hypersurface, I can basically formulate them on Scry plus and Scry minus, and technically, it should be enough providing some junction condition on the junction sphere. If we believe the evolution problem by Sachs, the characteristic evolution problem by Sachs, it's sufficient. So if you know basically the dynamic of gravitational data on one null hypersurface, a second one is what happens at the. For me, this infinite power of and I will not call them flux balance laws. There are just two flux balance laws, which are these ones. The other are constraint equation that makes the Einstein equation working well. Because of what? Because the boundary gauge is not foliating properly the space-time. You have a time and a null coordinate. So you have at each order you have to adapt your foliation to remind the system that yes, I'm time-like, I'm time-like, I'm time-like. That's for me the role of these equations. But I don't see from a purely Carrollian point of view from where this Newtonian equation to take the nomenclature of Marius, where they will be coming from. That's why I have to say that for the moment, I don't care. But that's a very interesting question.
Somebody else?
Another question I had was about invariance under small gauge transformations. So these nether charges for these large gauge symmetries, conserved or flux balanced, whatever they satisfy, can we at least show that they're invariant under small gauge transformations, small diffeomorphisms?
So the diffeomorphisms that are uncharged.
I'm just wondering if having picked Bondi gauge, diffeomorphisms that are uncharged.
Yes, exactly.
Having picked Bondi gauge, have we made a strong enough gauge condition that there are no small diffeomorphisms. Is there some sense in which you can show that they're invariant under small diffeomorphism so that the choice of Bondi gauge isn't that important?
Exactly. So, okay, the thing is that here in this construction, I didn't specify the gauge. So basically, all the diffeomorphism at the boundary, all the Weil transformation, all the local Carrollian transformation are symmetries. Now, when you fix a gauge, so I have a slide. I'm really sorry, Simon, but since the questions are there, I have to spoil your talk. So yes, so if you impose the BMS gauge fixing, which I will explain in a minute, you will have that, in fact, all your parameters will now depend on the diffeomorphism parameter. So the thing is that you will heavily reduce the class of symmetries you have at the boundary, basically by setting that when you perform a diffeomorphism, you will perform at the same time a local Weil transformation, a local Carroll boost, and a local rotation. And the parameter, I didn't reproduce the expression here, but they are clear, right? So in that way, for instance, you can show that the shear, which is a piece of the connection, which is exactly this piece, transform as follows, and which is not bizarre, actually. It's a perfectly acceptable Carrollian variation. So what does it mean to choose a gauge at null infinity? So to choose a gauge is basically, as usual, when you are working the Cartan formalism, to choose a Cartan frame. Here, if you want to go BMS, for instance, you choose the Cartan frame such that the clock form defines for you a function, which you call U, and also you can safely choose that, it has been explained already by Ashtekar and Gerhoch, that you can take because it's Carrollian, you can freely take the horizontal frame to be time independent. Up to basically breaking a part of the symmetry, but you don't care because BMS obeys these equations. And you see that that's a complete gauge fixing. Why? Because I have three constant equation on three vectors. So it's fine. I fixed it. And this is a good, what I would call a good gauge fixing. Okay?
But
And in that way, everything that I derived is BMS invariant as usual, because I recover the same equation. These equations are BMS invariant, and all the BMS momenta and hypermomenta transform as prescribed by the phase space.
okay.
Everything goes well.
So you are able to do things without choosing Bondi gauge at all, right?
Exactly.
That's what okay, very nice.
Yeah,
very nice.
yes.
Can I say that maybe this reflects some sort of kinematic, non-dynamical specific theory?
Why it's non-dynamical? I don't get the.
Sorry?
They're asymptotic these things like.
Yes.
Okay.
Yes, exactly. The equation that I have are asymptotic.
Maybe I am too focused in something that I have in mind. Sorry.
So was it your question? Sorry, I didn't get.
I have the feeling that BMS symmetry is a sort of kinematical symmetry where you can put theories on them. That's.
I will not say that because the thing is that when you consider so maybe it's not as strong as an argument for you, but when you consider, for instance, the gravitational scattering and even merging of black holes, you have a lot of multipolar momenta that are turned on, and this transform non-trivially under BMS, and each of them actually. So you have some dynamics encoded into this BMS chart. If you just have Poincaré, basically, if you just have Poincaré, you break an important symmetry, which is the Carroll boost symmetry at the boundary, and this Carroll boost symmetry is associated to a tower of charge that is usually not vanishing and encodes physics.
Maybe this is related to a work by Yannick and Xavier, where they consider the supermomenta has a hard part and a soft part in some sort of kinematical way, not depending concretely on the theory. But in a theory, you have.
Yeah, but I think it's not a proper distinction with what I have here, because what they merely did is to rephrase in more mathematical terms the split between hard modes and soft modes in the dynamical variables, which is the shear. Here, shear I'm considering contains all the modes, the soft and the hard, so it's not. And their shear, I hope for them at least, transform like this when the source modes are encoded into this term. So I don't see any contradiction with their paper, but maybe we can discuss.
Okay, maybe I'm wrong. Other question? Okay, thank you.
Thank you.
Adrien.